Okay, so remember where we left off is we had defined the cutoff frequency so that if I evaluate the transfer function at the cutoff frequency and look at the magnitude of this, this is 1 over the square root of 2 h max. And sometimes I put the magnitude, sometimes I'll let that go there. Well, let's look at what's really going on here on why I would possibly do this here. So I'm going to look at here an output here. So I'm going to have some input and some output here. So I'm going to have V in at j omega. Now again, remember here, I haven't maybe emphasized this, our transfer function's in terms of s, but you can literally plug j omega in for s. Okay? And we've talked about that before. So V in at j omega and V out at j omega. And then we have h at j omega, which is V out over V in. So we can get that V out at j omega is equal to h at j omega times V in at j omega. Now we're going to apply this definition. So if I apply this definition here, I'm going to substitute here the magnitude of V out at j omega c, and this would be equal to 1 over square root of 2, and then we call this h max, times the magnitude of the input voltage, and I'll just say at j omega c for now. But this here is the maximum value of transfer function. So what I'm actually getting here is I'm getting that the magnitude of the output voltage evaluated at minus j omega c is equal to 1 over the square root of 2 times the maximum output voltage. Because if this is max here, the input is constant. You know, for instance, it might be, let's just say, sine of 1000t, or cosine of 1000t, so we have no phase shift. Cosine of 1000t. So that's a constant. That's our input. We might change the input, and in fact we will. The whole point is to look at what happens with respect to frequency, but now we're picking one specific frequency, and the specific frequency we're picking is the cutoff frequency. So that's just a constant, and then if this is already at its maximum, well, that means I have to have V out max here. Okay, so that's got to be the maximum of the output voltage that we get here. Now, let's just substitute this in here. Let's compute power. Now power here would just be, and we're going to assume non-RMS, would be and I'll write it here as complex power here. We actually are just going to look at the average power. Actually, I'll just look at the average power. Compute, we'll say average power. So P at j omega c would be 1/2 the output voltage magnitude of the output voltage at j omega squared. And since I'm looking at average power, even though I know this could have capacitors and inductors, since you're looking at average power, you're only looking at a resistor component, because remember, resistors give you average power, and capacitors and inductors give you reactive power. Okay, so now let's just do some computations here. Well, wait a minute here. What we're plugging in here, so really, and this should be VC, not omega, omega C here. There should be a C here. Now it looks like I just put some random thing there. There we go. So if we do this here, substituting this in here, we get 1/2 times 1 over the square root of 2 V out max squared divided by 2. But then this is just simply equal to 1/2 times another 1/2 V out max squared over 2 over R, but wait, 1/2 V squared over R is equal to power, average power. So that means this term right here is my max power. And so we get then the end result, which is really why we define the cutoff frequency specifically. Now we could have gone backwards. We could have defined it with the result we get here and then see what effect that has on the circuits, but we defined it this way here. So what we get here is P at j omega c is equal to 1/2 P max. So the key thing here, I'm going to star this here. The cutoff frequency is at half the maximum power. Now that makes sense as far as the definition. How would you want to define something? Well, we could say a cutoff frequency, the signal being at 1/2 the power. Now let me ask you here, why do we do 1/2 power instead of, let's say, 1/2 voltage or 1/2 current? So why do we do the 1/2 power as opposed to it? Well, if you think about it a little bit here, the name kind of gives it away. Remember, voltage, some people always get this mixed up. Voltage is not power. You can have a huge amount of voltage, and an example of a huge amount of voltage is a static shock. A static electric shock is in the tens of thousands of volts. So you're getting, quote, tens of thousands of volts passed across your body with a static shock, but it's at extremely low currents. So there's not really much power behind it. Now there's enough power behind it that you feel a little shock, you know, but I mean, it's not like it's, you know, oh my gosh, it's gonna, you know, kill me, you know, just getting a static shock. So voltage in itself, having huge voltage doesn't mean you have huge power. Same way, just having huge current doesn't mean you have huge power. You could have a lot of current but very little voltage. Power is the idea of how much, I like to think of it as how much force is behind something. Um, it's not an exact parallel to it, but it's a close one. And if you think about it, if you've ever listened to some radio stations, and I know that's kind of getting a little old now. I don't even listen to radio stations anymore. In my car, I just listen to my cell phone music. But if you actually do listen to radio stations, sometimes they'll broadcast, they'll say something, broadcasting from Fort Wayne with, 20,000 kilowatts of power or something like that, and they'll say like, what the broadcast strength of the signal is at their location. And you've all experienced this if you've listened to radio again. As you drive further away from, for instance, Fort Wayne, you're eventually going to lose that signal. You're going to lose that station, and that's because the power of the signal can't carry it any further. And that's when it starts getting staticky, because what you're doing is you're picking up noise at the station as opposed to, actually a signal. And so that's why we would define it as 1/2 power, because power is really, as far as giving us, if you want to think about strength of a signal, power is going to give us the strength of the signal. So that's why we're interested in 1/2 power. Now, in the next set of lessons here, we're going to start analyzing some circuits, looking at some very basic filters. The first filters we're going to look at are passive filters. They're going to be first order, and believe it or not, they're only going to have 2 components in them, and we'll be able to get a filter out of them. Which is, I think, is pretty exciting. And we'll do some circuit simulations with those, as well as some example problems and design problems. Design problems are really easy when you're talking about these first order passive filters, so there's not really honestly that much going on with it. But we will pick that up in the next video.